like their atomic and physical properties, the chemical properties of transition elements are very different from those of the main group elements. One being that transition metals have multiple oxidation states versus just one or two like we see with our main group elements, okay? So what are oxidation states and their rules? Well, we got to remember from Chem 101, the oxidation states are going to indicate the degree of oxidation or loss of electrons or reduction, gain of electrons that an atom has undergone, okay? So there are specific rules that you can follow. Of course, I kind of brought these kind of small rules from the Tyler DeWitt group. Also, you can see rules from chapter 4.2 in your book. It's all about helping us get those oxidation state numbers so that we can go further and use them in redox reactions if we'd like. Now, we know with transition metals, they love to, again, lose the NS electrons first, like we just saw with electron configuration, okay? So the most common oxidation state that we normally see with transition metals is going to be that +2. But again, they can have multiple oxidation states and multiple stable oxidation states, all because of those incompletely filled d orbitals. So it's all about the electron configuration and how many electrons are in those d orbitals and if they are filled or unfilled. Okay, so if they're unfilled, then they definitely have more abilities to be a part of reaction. Okay, and then we do have this little table here that's going to be our oxidation states and then the different period for elements as you see here. Now, when it comes to the first 5 elements here, the maximum possible oxidation state is going to be related to the loss of all the 4s. You got to lose all 4s and 3d electrons. And so that means that if they have unpaired d electrons and all of the s electrons are going to be lost, that tells you the maximum oxidation state for these first 5 elements, for example. Okay, of course, you can look at other elements and their different oxidation states. I just want to kind of clarify for those first 5. You also will see from this table most common, which is most stable, and less common, which is less stable. Which goes to show you that although transition metals have the ability to make higher oxidation compounds, it doesn't mean that they will. So for manganese, for example, it has a stable in +7, +4, and +2. Iron is usually +2 or 3. Copper is usually 1 or 2, for example. Zinc is usually 2. And so you kind of can see that a lot of these different transition metals will have common oxidation states that we also will see in our compounds in the lab, for example. So just like some of those oxidation states gave us color, which we talked about earlier, we can use those oxidation state numbers to help us see what kind of colors different compounds would be, and also, again, use them for different types of reactions and redox reactions. Now, just to briefly talk about oxidation state rules, it's just like, for example, if you have an element that's by itself, like say you have O2, right over here, O2, the oxidation number would be 0, because anything that's elemental will be a 0 oxidation number. And so it's just little rules like that that you definitely have to go back and review. And so although this is a flashcard moment, you can go back and just add little details to your flashcard like, hey, what is oxidation rules? Let me go back and add a flashcard about that, for example. Let's go ahead and see this in practice and use this as our chance to review instead of just me just jumping in. Let's go ahead and use it in practice, do our best to understand in detail. So for our example here, the first one, it says determine the oxidation state of cobalt and CoBr2. So we're looking for this transition metal cobalt. What is the oxidation state of zinc and ZnCO3? And also what is the oxidation state of silver and Ag2S? So the first thing that we want to do is just make sure that we are using the rules for the oxidation numbers. What we can do is go ahead and use these rules, whichever kind of way you remember them, to help us figure out the oxidation numbers of elements that we know in the overall compound. Once we have elements that we know in the overall compound, we can use that to help us solve for a variable of what we don't know. Okay? So for example, with CoBr2 here, we know that bromine is going to be a halogen, and halogens usually have a -1 charge. So we can automatically say that this has an oxidation number of -1. We also know that this entire compound is neutral, so this entire compound is equal to 0. Now, when you have compounds that have a charge attached to it, you have to make sure that you set your compound equal to 0 when you're doing these type of examples, okay? And I'll give another one of those later on. Okay, you see I have added this compound here, MnO4-, so that means this compound actually has a charge, so you would have to set this whole entire thing equal to -1, okay? Now again, CoBr2, Br is going to be -1, this whole thing is set equal to 0. We're going to go through and make sure I figure out all the different elements that I know a charge for to help me figure out what I don't know the charge for. So let's go ahead and look at this ZnCO3. So a lot of folks will look at this and say, okay, there's 3 separate elements. But remember, our CO3 is actually the carbonate polyatomic ion. So it is going to be a 2- charge. And so anything that already has a charge, then we can basically just use that to our advantage for oxidation numbers. This whole thing is equal to 2. Okay. And then for Ag2S, we know that sulfur is in the same group as oxygen. So if oxygen is usually -2, then sulfur is usually going to have a -2 oxidation number as well. And this whole thing is equal to 0. Now down here, we know that our oxygen is normally going to be -2 unless it's attached to some exceptions, but it's not attached to any peroxides, so we don't have to worry about that. It's just attached to manganese. And this whole thing is going to be equal to -1. So again, you're just kind of locating where things are as far as you understanding where they are in your oxidation rules, okay? And then you want to just focus on what you want to set everything equal to, whether it's a neutral compound or not. Make sure you can identify polyatomic ions. And then all you have to do is just use algebra to find out what you don't know or your answer. So let's go ahead and get into that. So for example, back up to COBr2. Because we don't know what CO is, we can set that as X. Now we're going to add that to what we do know. So there's 2 Brs. What's the charge of Br? -1. This entire thing is equal to 0. So we have X minus 2 is equal to 0. Add 2 to both sides. Therefore, X is equal to +2. So that means our CO is equal to a +2 oxidation number in order to be a part of this compound, this neutral overall compound. Let's continue on with the ZnCO3. So again, we already said that our carbonate is going to be -2 here. So we would just go ahead and use that to our advantage. Let's go ahead and do our math. We're trying to find zinc, so that's going to be our X. Added to our carbonate, there's only one of them that has a -2 charge, and this whole thing is equal to 0. So X minus 2 is equal to 0. Going to add 2 to both sides. X is equal to +2 for our zinc. Great. Now let's continue on with different color here. So we are looking for our silver. Again, we know that our silver is going to be X, but there's 2 of them. So we have 2X plus 1 times a -2 charge for the sulfur is equal to 0. So 2X minus 2 is equal to 0. Okay, so we're going to add 2 to both sides. 2X is equal to 2. Divide 2 by to both sides. My X is going to be equal to +1. And so now my silver is therefore going to equal to +1 oxidation number. And finally, let's do the one down here. Okay, so we're looking for our manganese, which we're going to set for X. We have 4 oxygens that each have a -2 charge, and this entire thing is equal to -1. So we're going to have X minus 8 is equal to -1. Add 8 to both sides. My X is equal to +7. So my manganese is going to have a +7 charge. Or sorry, oxidation. Okay. All right, folks. And so this is how you want to kind of approach oxidation number. You'll see oxidation number and electron configuration as the main type of examples for your homework. So it's just, again, there to help you practice. If you don't understand, come back to this video. If you don't understand even smaller details, you want to go back and review one-on-one information. All right, folks.